All right, so now let's talk about the ideal gas law. The ideal gas law is another mathematical model that shows the relationship between pressure, volume, and temperature of a gas, but also the amount of moles or the amount of molecules in a gas. So this one is for describing the relationship not in between changes, not in between initial and final conditions of a gas, but just for any given gas. If we know some information about it, we can figure out the other variables in that gas. So, for example, or first let's talk about the formula. P is for pressure, V is for volume, N is the amount of moles of a gas of the gas, and T is temperature. R is a constant. It's a constant, and it equals um, 0.0821 liters atmospheres over mole K. 0.0821 liters atmospheres over mole K. So it's just a number. It's always going to be that number, and what it is just the coefficient that relates all these variables together. So you got to keep that in mind. And notice that the unit for the constant is liters times atmospheres over mole K. So if you're going to do any problems with this, you need to make sure your pressure is in your volume is in liters, your pressure is in atmospheres, and your temperature is in Kelvin. So the best way to go about learning this is to just work you through some problems on the study guide. Again, I'm trying to prepare you guys for the final. So let's do number 7. How many moles of helium gas is needed to pressurize a 100-liter tank to 255 atmospheres at 209 degrees Kelvin? Okay, so these are the conditions we want. We have a 100-liter tank, and we want to pressurize it to 255 atmospheres at 290 degrees Kelvin. So how many moles of helium gas do we actually need to achieve those conditions? So notice this has nothing to do with initial or final conditions. We just want to know the properties of some given gas. So that, guys, we're going to have to use the ideal gas law. PV equals nRT. What are we looking for? We're looking for the amount of moles. How many moles? Okay, so in that case, we need to isolate N, which is the moles, get it by itself. So we use some algebra to rearrange it, and we should get N equals PV over RT. Okay? So actually, let me move this, get some space to work. Okay, N equals PV over R and T. So what's our pressure? In this case, it's going to be 100 liters. What's our volume? Oh, I'm sorry. Our pressure is not in liters. Liters is volume. Our pressure is 255 atmospheres. Our volume is going to be 100 liters. R is a constant. It's always going to be the same number, 0.0821 liters times atmospheres over mole K. And our temperature, 298 degrees Kelvin. Notice all my units are in agreement with the units of R. They're all in liters, atmospheres, and Kelvin. If not, if the problem does not start off that way, you need to make sure you do the appropriate conversions. All right, so this is just a huge math problem to punch into the calculator. Just got to be careful how you punch it in, but it's going to be, let me punch it in my calculator here. 255 times 100 liters divided by R, 0.0821, and also divided by 298 Kelvin. And we get 1,700 1,042 moles. 1,042 moles of helium. You should see that Kelvin crosses out, liters cross out, and atmospheres cross out, and you get a unit in moles. So 1,042 moles of helium in a 100 liter tank will increase the pressure to 255 atmospheres at 290 degrees Kelvin, which is about room temperature. Here's our answer. We can also try number 8 here. At what temperature will 0.7 moles of oxygen gas exert a pressure of 5 atmosphere in a 10-liter container? So you have a 10-liter container full of oxygen gas, and we want to know if there's 0.7 moles of gas in here, and we want to know how much we need to heat it to in order for it to exert a pressure of 5 atmospheres within that container. Okay, so that's what the question is actually asking. And again, this has or it's not, we're not even heating it, just says at what temperature will these conditions be true. So again, this has nothing to do with change. There's no initial or final conditions. So we know we're going to have to use the ideal gas law. PV equals nRT. Another tip, something that tips it off, is that we're looking at moles. When moles is a factor in the properties of the gas, then we need to use the ideal gas law, because that's the only one that takes the amount of moles into consideration. This case, we're looking for, we're given certain conditions, and we want to know at what temperature those conditions are true. So we're going to have to isolate T, get T by itself to figure that out. So we do a little bit of algebra. We'll get T equals PV over nR. Okay. So our pressure for this gas is 5 atmospheres. Our volume is 10 liters. N, our moles, is 0.7 moles. And R is 0.0821. It's a constant, always going to be the same. And our answer should be, I have to punch this in the calculator. Sorry, let me do it real quick. 5 times 10 liters divided by 0.7 moles divided by R. And you get a temperature of 800. Okay, let me bring this down. Ignore that problem. I'm just going to use this space. T is going to equal 870 Kelvin. And so moles should cross out, atmospheres crosses out, liters crosses out. We're left with a unit of Kelvin. Punching this in the calculator gives us 870 Kelvin. So at 870 degrees Kelvin, 0.7 moles of oxygen will exert a pressure of 5 atmospheres in a 10-liter container.